So we're going to work with a family of sets in this problem. So we're going to let F be a family of sets, and A is going to be an element of F. So A itself is some set. And what we're going to do in this problem is we're going to show that A is actually a subset of union F. So that's what our goal is. To kind of just make a concrete example here so we can kind of visualize what's going on, let's actually write down a very specific value for F and compute what union F is. So let's write down F. F is a family of sets, so itself is a set, so we start off with a curly bracket, and every element of F is some other set. So for instance, maybe it has the set with elements 1, 2, 3 in it. It could also have a set with elements A, B in it. Maybe it has a set that's actually just a single element, so we'll say 7. And maybe it has another set with elements R, K, and 2. Okay? So this is an example of a family of sets. F is a set, but every element of F is also a set. In this specific case we're looking at, the family of sets F consists of 4 different sets inside of it. Okay. So what if we computed union of F? What does this mean? Well, computing union of F means take every element of F and union them together. So we would take the first set, union with the second set, union with the third set, union with the fourth set. And now I can just look at this and write down what this is. The union of sets is just all the common elements. So if I find all the common elements, this turns into the set 1, 2, 3, 7, A, B, R, K. So that's what union F would be in this specific case that we're creating here, just to get a little intuition about the problem. And from looking at this example, we can see that no matter what A I grab, so no matter what set that I grab out of F, so whether that's the set 1, 2, 3, or whether that's the set AB, or the set 7, or the set RK2, no matter which one I grab, any X in the set that I grab is also in this union. For example, what if I grabbed the set 1, 2, 3? So if I grab the set 1, 2, 3, so now A is equal to 1, 2, 3, any element inside of A, whether that's 1 or 2 or 3, that is in union of F. There it is right there. 1, 2, and 3 are all in union F. Or what if I grabbed the set RK2? So in this case, if I grab A and let it be RK2, any element of A, whether that's R or K or 2, those are all in union F. So what we've seen here with this concrete example is that A is a subset of union F, because no matter what A I grab, any element of A is an element of union F. So that's not a proof, but it gives us a little intuition for kind of what's going on here. So let's actually do the formal proof. We're given a family of sets F, and we're also letting A be an element of F. Let's let X be an arbitrary element of A. Since union of F is just a union of all sets in F, so obviously this includes the set A, then X has to be in union of F because X is in A. So that's the proof. It's pretty simple. Since X was in A, and we showed that this implies that X is in union of F, this is the definition of a subset. If for an arbitrary element of one set you can show it's in the other, this means these sets are subsets. So we have shown that A is a subset of union of F. That was our goal. There's kind of another way to work through this problem. I kind of call it the transformation method. If you're having trouble getting going on a proof, this is sometimes a good way to do it. You basically write down what you're given. In this case, we're starting off with F, a family of sets, and A is an element of the family of sets, and then you just write down the goal. So the goal is A subset union F. So nothing unique here, we're just writing down the problem statement, but trying to clearly state what our assumptions are, the givens, and what the goal is, what we're trying to get to. Then what we do is we, just one small step at a time, we transform the goal into something that's easier to work with. So the first thing I'm going to do is I'm going to write down my givens just as they are, and then I'm going to transform this goal one step at a time. So for instance, I'm going to ask myself, what does it mean for A to be a subset of union F? Well, what is the logical equivalence of this statement in terms of other notation? That means for every element, for all X, every X in A implies X is an element of union F. So this is just what it means to be a subset, just in a different notation. Once I've written it this way, this kind of gives me a clue what my next step is. My goal now is for all x, x in A implies x in union F. The for all there is a big clue. That tells me I need to let x be an arbitrary element because I'm trying to show that this statement is true for all x. So on the next line, when I write down my givens, I'm going to start with the 2 I have, but I'm going to tack on x in A because my goal was for all x in A. So I'm going to go ahead and say, hey, let's let x be an arbitrary element of A. And now I can rewrite my goal. I've already let x be an element or an arbitrary element of A. So now the only thing I need to show is that x is an element of union F. So I've kind of simplified it, my goal. Okay, same step. Let's rewrite our givens. And let's simplify the goal. What does it mean for x to be an element of union F? Well, let's think about that. That means that there's some set in F, and we'll just call it B. So there exists some set B in F such that x is an element of B. Right? That's what it means. If x is an element of union F, that means when I created that union, there had to be at least one set that x was a member of it. So we're going to call that B. So there exists B in F such that element x is in B. So now this is really easy. So I've transformed my goal into this new thing, and this is all I'm focused on now. I'm trying to show that there exists a B in F such that x is in B. This is now really easy to show. I'm trying to come up with any set in F that has x in it. Well, guess what? I've already written that down. I've already found a set, and that set is A. We've already said that A is an F, and we've also already said that x is an A. So showing that this statement is true is very easy. I just let B equal A. So at this point, I am done with the proof. And this set of steps kind of helps you see what you need to write down for your proof. The final set of givens here, let F be a family of sets, A and F, X and A, and now you have a very simple goal to reason through. And the thing that we reasoned through was essentially what we said on the previous chart when we did the short proof. So this transformation method can sometimes be useful. One step at a time, transform your goal into something a little simpler until you boil it down to something that is easy to show, and that sequence is what you can use to really write your final proof.